Hello everyone, I'm Soundarya from EC Section C. Today my topic is estimating the specific heat capacity and heating of electronic sensor and devices. Introduction to specific heat capacity. Specific heat capacity is the amount of heat reduced to challenge the temperature of a unit mass of a substance by 1 degree Celsius. It is crucial for understanding how materials respond to heat, especially in electronic applications. Knowledge of specific heat capacity aids in thermal management strategies of electronic devices. Specific heat capacity. Specific heat capacity equals to energy required by mass. Specific heat capacity is the amount of heat energy essential to rise the temperature of 1 kilogram of matter by 1 degree Celsius. Importance of heat management in electronics. Effective heat management extends the lifespan of electronic devices and sensors. Overheating can lead to reduced performance, failure, and safety hazards. Understanding thermal properties can optimize device efficiency and reliability. Factors influencing specific heat capacity. Material composition, structure, and temperature significantly affect specific heat capacity. Different materials such as metals, semiconductors, and insulators exhibit varying thermal properties. The specific heat capacity is often temperature dependent, necessitating precise measurement method. Measuring specific heat capacity. Various experimental techniques exist to measure specific heat capacity, including differential scanning, calorimetry. This method chosen can depend on the sample size, temperature range, and desired accuracy. Accurate measurement is vital for applications that involve rapid temperature changes. Measurement of the specific heat capacity of a liquid by an electric method. Mathematical relationship. The specific heat capacity can be calculated using the formula Q equals to mc by delta T, where Q is the heat added, m is the mass, and delta is T is the temperature change. Rearranging the formula allows for the estimation of specific heat capacity from experimental data. Understanding these relationships is essential for modeling thermal behavior in devices. Heat equation Q equals to mc. Q is the heat charge, m is mass, C is specific heat. Estimating heat generation in sensors. Electronic sensors generate heat as a byproduct by their operation, influenced by current and resistance. Estimation of heat generation is crucial for preventing overheating and ensuring accurate readings. The thermal design must accommodate these heat generation profiles to maintain optimal performance. Heat sensor circuit. Thermal conductivity and its role. Thermal conductivity measures a material's ability to conduct heat, impacting heat distribution in electronic devices. High thermal conductivity materials are often used in heat sinks to dissipate heat efficiency. Understanding the relationship between specific heat capacity and thermal conductivity is vital for effective thermal management. Heat dissipation methods. Common methods of heat dissipation includes conduction, convection, and radiation. Each method has its own advantages and limitations depending on the application and environment. Effective heat dissipation strategies are essential for maintaining device integrity under load. Convection, the transfer of heat through a fluid caused by molecular motion. Conduction, the transfer of heat from one substance to another due to direct contact. Radiation, energy that is radiated or transmitted in the form of rays or waves or particles. Finite element analysis. Finite element analysis is a powerful tool used to simulate thermal behavior in electronic devices. By modeling heat transfer, design can predict temperature distribution and identify hotspots. This technique assists in optimizing thermal design before physical prototype. Case studies in electronics. Real world examples illustrate the application of specific heat capacity in the design of consumer electronics. Case studies can highlight success and challenges in thermal management. Learning from these cases helps inform future design choices. Advanced materials for thermal management. New materials such as phase change materials and thermal interface materials are emerging for better heat management. These materials can enhance performance by improving heat dissipation and stability temperatures. Selecting the right material based on their specific heat capacities is crucial for innovation. Impact of temperature on performance. The performance of electronic sensors can be significantly affected by temperature fluctuations. Understanding specific heat capacity helps predict how devices will respond to changing thermal conditions. Temperature stability is essential for maintaining accuracy and reliability in measurements. Future trends in thermal management. There is a growing trend towards miniaturization leading to increased heat density in electronic devices. Innovation in cooling techniques, including active and passive methods, are becoming more relevant. Future research will likely focus on improving materials and methods for heat management. Conclusion. Estimating specific heat capacity is fundamental for the effective thermal management of electronic devices. A multidisciplinary approach combining materials, science, and thermal energies. The multidisciplinary approach combining materials, science, and thermal engineering is essential for advancements in the field. Continued research and innovation will significantly enhance the performance and reliability of electronic sensors. Questions and discussions. Thank you for your attention. I welcome any questions regarding estimating specific heat capacity and heat of electronic sensors. Engaging in dialogue can help deepen our understanding of thermal management in electronics. Conclusion. Estimating specific heat capacity is fundamental for the effective thermal management of electronic devices. A multidisciplinary approach combining materials, science, and thermal engineering is essential for advancement in the field. Continued research and innovation will significantly enhance the performance and reliability of electronic sensors. Engaging in dialogue can be dependent on understanding the thermal management in electronics.